Still on topic 2C for AP Chemistry, Unit 2, we're going to talk about formal charge and some other items. The formal charge of each atom within a structure can be calculated using this formula below. It's the number of valence electrons around the atom, in a particular atom, that are free, minus the number of non-bonding electrons around that atom in the Lewis structure, minus 1/2 the number of bonding electrons around the atom in the Lewis structure. So an example of calculating formal charge for atoms in a carbonate ion, CO3 2-. So you have to do it for each individual atom. So let's start with a carbon atom. The formal charge is going to be the number of valence electrons around that atom in the free atom. So here we have it drawn. So carbon, as a normal atom, has 4 valence electrons, minus the number of non-bonding electrons. Carbons, in this instance, all of the electrons are bonding, so there's 0 non-bonding, minus 1/2 the number of bonding electrons around the atom. So the number of bonding electrons is 2, 4, 6, 8. So it's 1/2 of 8. So it's 4 minus 0 minus 4 is 0. You really want the 0 number at the end of it. So now we look at each oxygen atom, and we will look at this oxygen. That's the C double bond O oxygen. So oxygen has 6 valence electrons, minus, there's 4 of them, 2 on each one, that are bonding, minus 1/2 of the non-bonding, or the number of half of the bonding electrons around the atom in the Lewis structure, which is 4. So you have 6 minus 4 minus 2, which is 0. So for this oxygen, the formal charge is 0. So now we look at these oxygens that are in the C single bond O. So again, oxygen has 6 valence electrons, and the number of non-bonding electrons is 2, 4, 6, and minus 1/2 of the bonding electrons, so there's 2 electrons bonding there. And so we go 6 minus 6 minus 1/2 of 2 ends up as a minus 1, and this tells us something about this creature. We'll learn about that on the next slide. So formal charge is used in one of 2 ways. The first way is to suggest where charges may most reasonably lay. For example, where the 2- charge of the carbonate ion actually resides, that we were just looking at. It resides in the C single bond O bond. And so note that the total of the formal charge for each atom in there will add up to a 2-, which is the charge on the atom. Or formal charge could be used to help select the most plausible structure from a set of resonance structures. So example, determine the most likely Lewis structure for a CH2O. So you could have this, a C with 2 H's and a double bond O, or you could have a C with a single bond H, a double bond O, and then an H over here. So in order to determine which structure is most likely, choose the structure with 0 formal charges, and or formal charges with absolute values as low as possible, and or keep any negative formal charges on the most electronegative atoms. Since the first structure has no formal charges, it's considered to be the most plausible. So if you can draw a Lewis structure that uses all the valence electrons and fulfills the octets, do not seek an alternative or better structure with lower formal charges unless the question leads you down that path. Dative or coordinate bonding, electron-deficient species. Occasionally when drawing a Lewis structure, you might encounter a molecule with a central atom that does not have a complete octet of electrons surrounding it. One example is boron, in specific like BF3. In this molecule, the boron atom has only 6 electrons surrounding it rather than the usual required 8. The boron atom is said to be electron deficient. It can make up the octet by forming bonds with other compounds that have non-bonding pairs of electrons, especially things with nitrogen. Compounds tend to have these lone pair electrons. So the new shared pair or covalent bond formed is made up by using both the electrons from one species, in this case the nitrogen atom, and the ammonia molecule, rather than one from each species as in a normal covalent bond. This type of covalent bond is called dative or a coordinate bond. So you see this ammonia molecule walked up to this boron trifluoride and said, dude, let's bond. I'll complete your octet. Polar bonds and polar molecules. In order for a substance to be polar, bonds within the molecule must carry different charges. Example, a dipole moment must exist, and the dipoles that are present must not cancel out due to symmetry. The dipole moment can be indicated by an arrow that points towards the negative charge center with the tail of the arrow indicating the positive charge center, or by using delta plus and delta minus. Those are little lowercase deltas. For example, consider two pentanone and trifluoromethane that are both polar, like water, which is also polar. Opposite ends of the molecules carry different charges, and there is no canceling of the dipoles. Both of the compounds below are polar. Their shape does not cancel out the charge distribution. Nonpolar bonds and nonpolar molecules. Now consider hexane over here and carbon tetrachloride. Neither are polar molecules, but for different reasons. In hexane, carbon and hydrogen have very similar electronegativities, and as a result, the bonds are effectively nonpolar. In carbon tetrachloride, on the other hand, it has 4 polar CCl bonds, but because of its symmetrical shape, it is nonpolar overall. The partial positive charge is located at the center of the molecule, and the partial negative charges are equally spread around it, causing the dipoles to cancel. Examples of other compounds that are nonpolar as a result of symmetry and cancellation of dipoles are carbon dioxide and boron trichloride. So polyatomic molecules and hybridization of orbitals. When considering a polyatomic molecule, the question of shape must be accounted for. Outer shell atomic orbitals of the central atoms in Lewis structures are said to hybridize or undergo hybridization, a process of mixing. Consider the example below in the table of sp3 hybridization of carbon in the methane CH4 molecule. So hybridization. In its ground state, the carbon atom has 2 unpaired electrons, and as such, it may only make 2 bonds with hydrogen atoms to form the species CH2. However, this species is extremely unstable and does not exist. In order to form the much more stable CH4 molecule that does exist, one of the electrons in the 2s orbital is promoted into the empty 2pz orbital to form the excited state of helium 2s1, 2px1, 2py1, 2pz1. These 4 orbitals then mix to form the 4 sp3 hybrid equivalent orbitals. These 4 hybrid orbitals then form simple sigma bonds as they overlap with each other of 4 atomic s orbitals of 4 hydrogen atoms to give 4 electron pairs around the central carbon atom. Example, 4 covalent bonds in the familiar tetrahedral shape. In all the examples below, the terminal atoms join the central atom's hybridized orbitals using simple sigma bonds to form the final molecule. Hybridization is really easy. That sounded so complicated on the other slide. The type of hybridization present in a species is really quite simple to predict. By considering the total number of electron pairs, including both bonding and non-bonding pairs, around the central atom, one can determine the total number of orbitals that need to be present, since each electron pair needs 1 orbital. I'm so out of breath. So by taking, in order, 1s and as many p orbitals as required, up to 3, one can determine the correct number of orbitals needed and hence the hybridization. For example, 4 electron pairs, whether bonding or non-bonding, require 4 orbitals and have a hybridization of s, p, p, p. So 1s, you can only have a max of 1s, and you can just have a max of 3p, so sp3, so those add up to 4. Other examples. Methane, CH4, has 4 things on the center. I just count the 4 things on the center, and so it needs to add up to 4. So you could have 1s and 3 p's, and it would be sp3. So in H3, I have 3 H's, but I also have a set of lone pair electrons if you were to draw the Lewis structure on the N. And so those are 4 things, and 4 items add up to 4. So 1s and 3 p's adds up to 4. CO2, it just has 2 things on the center, 2 oxygens. There's no lone pairs on the C, so 2 would be 1s and 1p. Blah, blah, blah. So sigma and pi bonds. Consider 2 hydrogen atoms forming H2. Each hydrogen atom has 1 electron that occupies a spherical 1s orbital. On forming H2, these 1s orbitals overlap to share a pair of electrons, forming a molecule and a covalent bond. Now consider 2 oxygen atoms forming O2. Each oxygen atom has the electron configuration of 2s2, 2p4. The 2 dumbbell-shaped 2p orbitals that are incomplete can take part in bonding, and there is a simple end-on-end overlap that occurs. The electron cloud density is located along the axis of the bond, and this is called a sigma bond or covalent bond. There is also scope for another type of bond that occurs from the sideways overlap of the other p orbitals. Here the electron cloud density is located above and below the axis of the bond. That is called a pi bond, p pi. As a result, the oxygen atoms form a double bond, giving the familiar oxygen molecule. Double or triple bonds. Whenever a double or triple covalent bond is formed, the first and strongest bond is always a sigma bond, and all bonds after that are considered to be pi bonds. Pi bonds lead to delocalized electron clouds via the overlap of F unhybridized p orbitals, giving rise to the potential for some electron movement and for the occasional occurrence, although rare, of molecular substance that can conduct electricity. Sigma bonds can freely rotate, but pi bonds and alkenes prevent the rotation of carbon bonds, leading to the existence of cis and trans isomers. Were those distilled by chance? Can I just have distilled? No, I just need distilled water. Could you do that? Thanks. Sorry for the interruption. The carbon double bond cannot rotate because of the presence of the pi bond, so the CH3 groups remain fixed on the same side of the double bond cis, or opposite sides of the double bond trans. We learned a little bit about this maybe in organic chemistry in first year chem. So in butane, the sigma bond between the central carbons can rotate. There's no pi bond. So these two conformations are 100% interchangeable and are the same compound. They're not isomers. What in the world am I talking about? So molecular orbital theory. There is another approach used to explain bonding molecules where simple Lewis and Vesper models fail to account for the observed behavior of molecules. Another more complex theory must be used. One such example is the unexpected paramagnetic behavior of oxygen. Its bonding can be explained using molecular orbital theory, which describes covalent bonds in terms of the combination of individual atomic orbitals to form molecular orbitals rather than independent overlap of individual atomic orbitals. That's the end of our 2C topic.